The notions of probability, length, and mass have a very similar structure. To begin with, they're all assignments of non-negative values. Notice, for instance, that the probability function assigns a non-negative value to an event occurrence. So, for instance, you can say that the probability of rain is 50%. A length function, or better, a length in meters function, assigns a non-negative value to a line segment. So, for instance, you can say that the length in meters of a piece of fence is 100. And a mass function, or better, a mass in kilograms function, assigns non-negative values to physical objects. So, for instance, you can say that the mass in kilograms of the Earth is 6 times 10 to the 24. Something else that these notions have in common is that they're all additive. So the probability that either of two incompatible events occur is just the probability that the first one occurs plus the probability that the second one occurs. The length in meters of two non-overlapping line segments taken one after the other is the length in meters of the first plus the length in meters of the second. And the mass in kilograms of two non-overlapping objects taken together is just the mass in kilograms of the first plus the mass in kilograms of the second. Notice in contrast that the notion of temperature is not additive in this sense. It's not generally the case that the temperature of two non-overlapping objects taken together is the result of adding the temperatures of the individual objects. In this lecture, we'll talk about the notion of measure, which is a very abstract way of thinking about additive assignments of non-negative values, such as those corresponding to probability, length, and mass. We're also going to talk about non-measurable sets, sets so weird that they cannot be assigned a mathematically respectable measure. Non-measurable sets have some very unusual properties, and they can be used to prove some pretty remarkable results. For instance, the Banach-Tarski theorem, which shows that it's possible to divide a ball into a finite number of pieces and reassemble the pieces without changing their shape or their size, so as to get two balls, each of them of the same size as the original. It sounds impossible, and yet it's true. That we're going to prove in the next lecture.